you can give me, Jamie?
55 from chapter 5 in the textbooks problem section.
Okay, let me pull that up. I actually have the book open right now, and you say 55 from chapter 5.
Yes.
Okay, so I'm looking at 5. I'm thinking that's probably going to be in the general problem section since it's all the way up to 55, but it might be just before that. Let's see. Yep, it's just before that because the general problem started at chapter 80. So now I'm going to that. Darn it. We'll do it again. I'm pulling it up right now on a different screen. Y'all aren't supposed to be seeing this. So that's don't worry too much. So we're looking at like 55. Okay. A bug walks outward from the center of a turntable that is rotating at 65 RPMs. If the coefficient of static friction between the bug and the turntable is 0.42, how far out from the center does the bug get before it starts to slip on the turntable? All right, this actually looks like a good one to share. So I'm going to do a share screen, and I'm going to admit that person too. And I'm going to share this one. Okay, so here's the problem Jamie's discussing. A bug walks outward from the center of a turntable that is rotating at 65 RPMs. The coefficient of static friction between the bug and the turntable is 0.42. How far out from the center does the bug get before it starts to slip on the turntable? What happens to the bug after it moves farther out past that point? So is that the one you're talking about? Because sometimes they're misnumbered from the MyLab system versus the other system.
Yeah, that one didn't make any sense.
Okay. So basically what you're doing is a bug is making its way out farther and farther towards the end. But in doing so, the bug is actually moving faster and faster because at all times for it to make a circular orbit around the center of the record player, it's going to have an acceleration towards the center of v squared over r. And because you're going out, the velocity is increasing. So they're saying the center of the turntable is where it's walking from. It's rotating at 65 revolutions per minute. So that's actually an angular speed that could be measured, for instance, in degrees or radians per second, but it's given in RPMs, which means rotations are 360-degree intervals per minute. So you could multiply that 65 times 360, and that would be the number of degrees per minute. And then you could divide it by 60, and that would give you degrees per second. Let's see what's going on here. Oh, I got another person coming in. So that would be your angular speed. But because the bug is trying to walk outward, what you see is that as he gets further and further outwards, he's going to have enough friction to keep him from sliding outside, as well as enough friction to keep him moving forward tangentially, say. But I'm not really, let me see, hold on. What section is this corresponding to? Uniform circular motion. Okay. So I've got all the data that I need, 65 and 0.42. I got 4 more people in. Let's see that. So let's try to actually solve this problem and see what happens. So I'm going to stop sharing the screen. And what I'm going to do now is start sharing the screen again, but this time I'm going to share the screen with my iPad. Now it's right at 5:20, so this is time for the class to start. So welcome everybody. I am answering a question that one of our students had regarding problem number 55 at the end of chapter 5. What we're looking at here is a circle or a circular motion, say, of an ant crawling on a circle, and it's trying to walk outward like this. We have that I'm going to call it omega, is 65 RPMs. And what I would recognize that as is 2 Actually, I'm going to do it a different way. That is 1 revolution is equal to 2 pi radians. And of course, 1 minute is equal to 60. I don't want to do it that way because that's upside down. Sorry about that. It's per minute, so the minute's in the bottom. So I'm going to say 1 minute is equal to 60 seconds. And that actually allows me to convert the whole figure to radians per second, which is a good measure that always works with our equations. We just have to make sure, you use the right radius and stuff like that. So I'm going to do 65 times 2, and I'm going to keep it in terms of pi, and then I'm going to divide that by 60. So I'm getting 2.167 pi radians per second is the speed. The coefficient of friction is 0.42. Okay. And they're wanting to know how fast or how far out he can go before he actually loses grip. So how far out from the center does the bug get before it starts to slip on the turntable? So you're thinking that in order for the bug to go towards the center, if I look at the diagram from the side, this would be your record. This would be the center of your record. And your bug would be like this, say. Okay. That little bug has to have a force pushing this way, and basically enough to maintain. Actually, let me rephrase it. I should say the bug has to have a sufficient friction coefficient to accelerate towards the inside. So if I actually draw a coordinate system right here like this will be the x-axis and this will be the y-axis. Then what I have is a little bug of mass m, and the forces acting on the bug are the weight mg, also the normal force Fn, and in some sense, you've got to imagine it's kind of confusing because the bug is actually walking out, but in order to have sufficient friction, the bug has to actually have enough force to keep itself pushing in. So we're going to imagine the friction as pointing this way. And that friction is going to be mu times Fn. Okay. So the summation forces in the y direction equals mass times acceleration in the y direction, which is 0, shows you that Fn is just equal to mg. It actually is Fn minus mg equals 0. So that's one of the expressions we got. Now, the summation forces in the x direction equals mass times acceleration in the x direction. That's going to require mu times Fn, which we already know is mg. That's got to be equal to m times v squared over r, where r is the distance out. So r would be this distance here. So I can now say mu times m times g is equal to m times v squared over r. The m's cancel out. And basically they're wanting to know r. So what I can say is mu g is equal to v squared over r, which implies r is equal to v squared over mu times g. So what I also know is that v is equal to r times omega. You can see that from the equation that gives us radians. S is equal to r times theta. S is the arc length, r is the distance out, and theta is the angle you turn through. If I take the derivative of that with respect to time,
and assume the r is a constant, then you get d theta over dt. Well, this is just velocity is equal to r times omega. And actually, I shouldn't even put those vector symbols on it, so I'm going to take that off. But the velocity tangentially is equal to the r times omega. So I can put that in there as well. Now I can say r is equal to r squared omega squared over mu g. And what that tells you is that we already know omega. That's what we calculated up there. What that tells you is that cancel out this one with one of those. And now I've got r is equal to mu g over omega squared. So this is going to be 0.42 times 9.80 meters per second every second over 2.167 pi, and that's radians per second, and that's going to be squared. So r will force that full mu coefficient of friction to be 0.42 at that point. So what that point is 0.42 times 9.80. And then I'm going to divide that by parentheses 2.167 times pi. And then I'm going to square that stuff in the bottom. And that gives me 0.0881 meters. And you can see that from radians per second is really no units, but it's squared and it's in the bottom. So it'll become second squared over radians squared. The second squared in the top will cancel out with the second squared in the G. And that gives us, of course, 8.81 centimeters. So does that make sense, Jamie? I mean, I know it's probably something you hadn't thought of, but it doesn't necessarily mean that's a problem. The bigger problem is now that you've seen it, you should be able to sort of redo it again.
Yeah, I mean, could we have still gotten that if we used the formula like the V equals 2 pi r over t? Oh, we don't have an r.
You could use a 2 pi r over t if you wanted and solve for r, but you then have to convert this omega, figure out the way that that omega relates to the period.
Okay, so I have to look up omega stuff. Okay, then.
Yeah, it's a little premature for them to be giving you this much of this. If you see, when we look in our table of contents for our book, you'll see rotational motion starts in like chapter 9, no 10.
Okay, so this isn't needed. This part isn't going to be needed for the test?
I wouldn't say all that, but I would say this
I just mean the omega part.
Probability. Yeah, I'd say this problem has a low probability of being on the test. Let's put it that way.
Okay.
Okay. But yeah, I would definitely know, like, you know, how steep of a curve should be, or how steep a roadbed should be banked for a particular velocity curve, assuming no friction, stuff like that. That's more important. But when we're getting into the woods of talking about RPMs, and you got to work out the complexities of what an RPM is and how that's related to a velocity, that's a really good homework problem, but not so good of a test problem. Does that make sense?
Yes.
All right. So I guess we're 10 minutes into class. I'm gonna go ahead and get started on the new material. And the new material is actually kind of neat. We've left gravity now, and we're doing the chapter on work and energy. It's actually a really short chapter, at least the way I cover it's a really short chapter. The learning objectives are relate gravitational potential energy to the vertical position of an object and its mass. 7.2, relate elastic potential energy to the displacement of an object attached to a spring and the spring's force constant. And then 7.3 is apply conservation of energy. Apply conservation of energy to an object subject to only conservative forces. Apply conservation of energy to a subject of non-conservative forces and stuff like that. So they're giving you a lot of different things, but in reality, they're not really giving you any of that yet. For instance, section 7.1, we're talking about work done by a constant force. 7.2, we're talking about scalar products of two vectors. And 7.3, we're talking about work done by a varying force. And then 7.4, we're doing the work energy theorem. So the conservation of energy stuff really comes more in the next chapter. So let's start off by talking about physically, what does work mean in everyday life? Because I like, when I teach my physics classes, I don't like you guys to think how different these concepts are in physics from your everyday life. I like you to be more confident about the physics that you're doing because you already experienced those things in life. For instance, when I introduced average speed, I introduced you to your speedometer and the units, and you said the speedometer had units of miles per hour, and you recognized miles were a unit of distance and hours are a unit of time, and per meant divide. So you could think, oh, well, velocity is like dividing the distance by the time. And sure enough, that's what our formula was. The average velocity is distance traveled divided by time taken. So similarly, I don't want you thinking of work as some abstract thing. I want you to think of work as some thing that you're familiar with. So let us start by a little motivation. I'm going to draw, for instance, two lines. Here's one line. And this line is in fact 100 feet by 200 feet. And you have a lawnmower that has a blade that is 2 feet. Okay. Well, if you're obsessive compulsive like me, you're going to make sure you cut your lawn in parallel paths, and then you'll probably go back over it and cut it in paths perpendicular to those first parallel paths. But the big thing is, what you'd see is that this yard would require basically 50 trips north to south, say, or actually I should say south to north.
Professor.
Oh yeah, I'm not showing your screen, am I?
No.
It's so sad. It's just, yeah, this brain gets me back and forth to work. I haven't run over anybody. It's really great. Sorry, guys. Okay, ladies and guys, I should say. So 50 trips north to south. So what I'm going to do is say, this is my screen. This direction down here is north, and this direction up here is south, just because I said it that way. Now I got to do it. Okay, you can see, because it's 2 foot wide, 50 paths north to south is going to give me the width that I need. And each one is at 200 feet per trip. So if you multiply 50 times 2,000, 5 times 2 gives you 10, and then 0 times 0 gives you 1,000. So that's in fact 10,000 feet walked. So that's a typical scenario of what you're going to do to mow that lawn. Now let's see if we have a different lawn. Let's say this lawn's going to be 200 by 200, say. And again, you're going to use the same lawnmower that has a width of 2 feet. So now you're going to do 100 trips at 200 feet per trip, which in fact is going to give you 20,000 feet walked. Okay. So I think you would both agree, all of you would agree that the 100 foot by 200 foot is less work than the 200 foot by 200 foot lawn. Would you agree? I'm going to assume that the answer is yes. Okay. If that's the case, then you might reach the conclusion that work, well, let me actually do it this way. Work, which we recognize as a symbol W, is in fact proportional to distance. And I think y'all would make some sense out of that. Obviously, work is related to distance. And you might even make the conclusion if these two lawns were similar softnesses, similar steepnesses, similar grass, similar height of the grass, all that good stuff, you probably could reach conclusion that, in fact, it would take you twice as much calories and twice as much time to cut the second lawn compared to the first lawn. And that would be a direct relationship, that work is directly proportional to the distance of travel. Okay. Now, if you also, however, decided to cut the first mower or cut the first lawn with a particular mower and then the same mower, but you decide to cut the second lawn with a much heavier mower. So let's say second lawn mowed with 24-inch 100-pound mower, but first lawn is mowed with a 24-inch 50-pound mower. I think y'all would conclude that that second mower is going to be more of a pain than that first mower. Would y'all agree with that?
Yes.
Yeah. In fact, we know that the friction force is directly proportional to the normal force with some coefficient of friction. If these two lots were similarly manicured and leveled and softness and stuff like that, it wouldn't be unreasonable to think they'd have comparable coefficients of friction in case, and since they're fairly level, which we can assume, or they're the same level, which doesn't matter either way, you're still going to get the normal forces proportional to the weight. And since the weight is twice as heavy, we now reach the conclusion that work should also be proportional to force. And that seems kind of reasonable, right? The more force you have to put into something, that's the more work you have to do. So from there, we've got just our everyday definition of work. A bigger yard is more work than a smaller yard. A heavier lawnmower is more work than a lighter lawnmower. We might even reach the conclusion that, hey, if I'm pushing somewhat downward on the mower as I cut, so let's say there's two scenarios. I'm cutting just like this. That's one scenario. And then there's another scenario where I'm cutting and pushing down actually on the lawnmower like that. You see that this force and this force are quite different. In fact, that bottom force has a component that's parallel to the motion and a component that's perpendicular to the motion, whereas this one's just the force parallel. So, though in the second scenario, we might actually feel like we're doing way more work because we're putting some work into increasing the normal force and therefore increasing the friction force and therefore increasing the horizontal force that we got to apply, it would feel way worse. But we don't want to count that wasted force in the grand total of the total amount of work done. So in fact, what we'll say now is that work is actually proportional to the component of force that's parallel to the distance. And that would be an ideal scenario. That's really what you'd want, is you'd want to define work where it sounds like everyday life, i.e. it's proportional to distance traveled, it's proportional to the work you have to put into it. And we don't overcount because we're doing stupid stuff, which, pushing downward instead of purely horizontally is in some sense stupid, because, you're wasting some of the force in not moving it. Okay. So with that in mind, we get a formula for work, at least with a constant force, is supposed to be force. And we'll say this is I'll say F times D, like D is a vector. And then I'll say cosine of the angle between them, where let's say F is like this and D is like this, and this is theta, because then you see when I take and multiply F times the cosine of theta, I get F parallel. Does that make sense? So that is a way of looking at it. And this is for really a constant force. If we actually had a force that varies with time or position, we'd have to actually take into account the changing of the force along the path of travel. So that's a little bit bigger deal. So for a constant force, for a constant force, work is just going to be F times D times the cosine of the angle between them. That works just fine. And in fact, if you want to think about lifting a box of mass M off the ground, and I'm going to lift it up to some height H, okay, then I want to apply just the right amount of force to overcome the force of gravity. So my free body diagram would look like this. There's my x-axis. There's my y-axis. There's my mass M. And it's got a force acting on it, mg downward. And I got my force acting on it, F upward, like that, okay? If I did that and I did it just so I only give it enough force to overcome the weight, then some random molecule bouncing off the bottom is going to lift it a little bit. And I wait, and another random molecule is going to lift it a little bit. If I keep doing that, keep maintaining that force mg, a random molecule hitting the top is probably not going to move it. But a random molecule hitting the bottom can actually help it a little bit, right? So I do it basically infinitesimally slowly, so I don't give it any more speed. Then I can say the force is actually going to be equal in magnitude to mg, but in the opposite direction. So then I'd say the work is actually equal to m times g times the distance traveled, which we said is h. And of course, the force F and the displacement vector D are parallel. So it'd be times the cosine of 0 degrees. And in fact, what we get is work is equal to mgh. And that's actually something we define to be the potential energy. We usually use either the symbol U or P or PE for potential energy, and its quantity is M times G times H, okay? So that's what happens when you calculate the work with a constant force. In fact, the work done is actually equal to the change in potential energy, because that we move so slowly that we didn't actually increase its speed, which is another type of energy we could have gave it. But by moving it so slowly, we just got it up to the height h, but it had no speed. So all the energy went into lifting it. And in that case, the work went into the change in potential energy. The potential energy we could call zero anywhere we want. What we've done here is we've assumed that the potential energy was zero when it was sitting on the floor or ground, no matter what story it was on. And then once we lifted it to a height h, then the potential energy was 0 plus mgh. So the final potential energy is mgh, the initial potential energy is 0. So the change in potential energy is mgh minus 0. So in that case, we found work is the change in potential energy. And as long as we stay close to the Earth's surface, our gravitational force on us will be mg. So that force is roughly constant. If you start to get on the order of distance away from the center of the Earth that are 2, 3, 4 times as big as the radius of the Earth, then this formula is not going to work anymore. Okay. Now, we understand that. We can say, well, what is this new quantity called work? And what is this new quantity called potential energy? What kind of units do they have? Well, the fact that work gave us a potential energy tells me that work and potential energy has the same units. And in fact, the unit of this work quantity is actually equal to, we see it's the unit of the force times the unit of the distance times the unit of cosine. And remember, trig functions don't have any units because they're ratios of sides. So it's like meters per meter. So in this case, we get a Newton times a meter. Well, in fact, that is equivalent and defined to be the joule. So 1 Newton meter is defined to be 1 joule. And I usually tell people the story that there's actually a beer in Great Britain. As far as I know, I haven't been to Great Britain, but people have told me this. There's a beer there called Jowls. And that's actually the family of Robert, excuse me, I can't remember his first name now, of Joule, who made the discovery of the mechanical equivalent of heat. And basically, they worked on thermodynamics to understand how metals would change when heat's applied to them, for instance, in designing cannons and stuff like that. But they also manufactured beer and understood the thermodynamics of that. And lo and behold, now we still have a beer called Jowls, which is descendant of that family Joule. Okay, so that's the unit. But you might also remember in the CGS system, which is centimeter gram second, the unit of force was called the dyne, and it was grams, centimeters, grams, whoa, no, grams times centimeters per second. Well, that was defined to be the dyne. And you can already tell that 1 dyne, notice the Newton is a kilogram meter per second. So the Newton is 1,000 times larger because of the kilogram instead of the gram. And it's 100 times larger because of the meter instead of the centimeter. So in fact, 1 dyne should be 10 to the negative 7th newtons. Or another way of saying it is 1 Newton is equal to 10 to the 7th dyne. And that's where we get terms like dynamometer, okay? But it also turns out that, in fact, in the CGS system, the unit of work would be the dyne times the centimeter. And the dyne times the centimeter is actually something called an erg. So you've heard of phrases like ergonomics. That's where that came from. Erg is a unit of energy. And in fact, the erg is such that, actually, this should have been a 5th. Sorry about this. Let's check that real quick. I jumped ahead when I wrote 7 there. I worked out the math and said what was right, but then I wrote what was wrong. So it's a factor of 10,000, or excuse me, of 1,000 for the kilogram and a factor of 100 for the centimeter. So that should have been 5 zeros. So that's 10 to the negative 5th. And that's the same thing with the other one. That should have been 10 to the negative 5th. So
this should be 10 to the 5th here, and that's dyne. And this is 10 to the negative 5th. And that's newtons that way. Okay. Now, where the 10 to the negative 7 came in is in this erg, where 1 erg is actually equal to 10 to the negative 7 joules, or 1 joule is equal to 10 to the 7 ergs. And then a fraction of an erg, like something like 0.76, I can't remember the number, is a foot-pound. So that's the British system that's used, even though we're not going to mess with that at all. So anyways, that's our units. We've got that settled. Now what I want to talk to you about is, what if the force actually changes? So you can do an example of this if you really wanted to. You can just say, okay, let's say a 10 kilogram object is lifted a height of, let's say, 10 meters. So a 10 kilogram object is lifted a height of 10 meters. The work done would be m times g times h. Well, m is 10, g is 9.8. So I got 98.0 newtons is the force. And then multiply that times 10 meters, and I got 980 joules. So lifting a 10 kilogram object 10 meters requires 980 joules. Simple example. That's why I'm not taking much time to do that. Now I'm going to work with a non-constant force. So work for non-constant forces. So what you're going to do in this scenario is, you might imagine that you're carrying this object on a little adventure, okay? And obviously your force is going to change, either as a function of position or as a function of time or something like that. So what you do is you divide this little path up into very small little segments, so that it's basically a straight line over the whole part. And if that's not good enough, if you still find that the force varies too much over one of those small distances, then you're going to make the distances even smaller, until you get not only that the line looks close enough to straight, but also that the force looks close enough to constant. And what decides on how small that should be is how many decimal points you want, basically. Okay. So if you do that, then you could say, here, right here is a particular portion of the line, and that portion is going to be called DL, and it points in the direction of travel, say, along the path that you're taking. And at the particular point, say the left side point, it's actually tangential or parallel to your path at that particular point in time. As you can tell, there's very little curve from, let's say, this part of the line segment and this part of the line segment. So it shouldn't matter too terribly much. Now, what we have to do is find the F at that position. And then what we're going to do is we're wanting to actually find the component of F that is parallel to that DL there. So it can just be like a normal constant force. I just multiply F times D, in this case DL, times cosine of the angle between them. Well, I have to do that for possibly an infinity of little points. So it turns out that this work is going to be equal to the integral of F dot DL. And this is actually very special. This is not just a integral, and that's not just a multiplication symbol in there. That is your actual dot product from trigonometry, and I'm going to review that in a second. And this is what's called a line integral. Most Calc 3 courses never get to this part, but that is a portion of what Calc 3 is about. It's supposed to be about vector calculus. And in vector calculus, we do things called line integrals, surface integrals, we do curls, we do divergences, we do gradients. But most of our students aren't as experienced with the calculus when they come in. So we normally have to, even if they were lucky enough to have calculus in high school, they usually don't have that great of a grasp of it. So we still got to go over some of the original stuff. But if you're at a really elite university where you can just randomly fail people if you want,
And I'm not saying they want to, I'm just trying to be facetious here. But if you were at like Princeton or MIT or Harvard or Caltech or something like that, there's a high probability that your Calc 3 course would actually get to vector calculus. They might even do differential forms and all sorts of cool stuff like that, but we very rarely get to it. That being said, you can still find it in your book. Okay, so you can look in there, but that's what we're going to do is we're going to have to learn how to do a line integral. Now, the good news is a lot of the forces we deal with in physics are what's called conservative forces. And conservative forces have this neat property, one, that their curl is 0, but because their curl is 0, that means the line integral from, say, some point A to some point B doesn't depend on which path you take from A to B. You can go straight line from A to B. You can go straight in the Y direction and then straight in the X direction from A to B, or you can go straight in the X direction and then straight in the Y direction, or you can go in little loop-de-loos and come back at B and you still get the same answer. So it turns out that a lot of people can get through this physics course doing line integrals without actually thinking about it being line integrals and still getting the right answers. Okay. I'm going to make sure you don't do it that way because you need to know how to do line integrals. And this is going to be the norm for engineering and science majors, is you're often going to learn your mathematics from your science and engineering teachers, whether it be chemistry or engineering or physics or statics or dynamics teacher or whatever. So let's really verify what's going on here by first talking about what a dot product is. Does anybody have any questions before I go on? Okay, I thought I heard somebody say something. So let's start off with a dot product a little bit, and then we'll go to an actual line integral to help us. So the dot product is also called the scalar product. And that's because if you take a dot product, you take it between two vectors. So it's vector A times vector B, say. And remember, there's ways you can write vectors, one of which is the easiest is this. You can say AX plus AY plus AZ in less than and greater than symbols. That's the same thing as saying AX I hat plus AY J hat plus AZ K hat. Similarly, we can write B is equal to BX comma BY comma BZ greater than. That's equal to BX I hat plus BY J hat plus BZ K hat. Okay. So it turns out if you follow this process, you can treat it just like a distributive property problem. You can say A dot B, looking at the second version, the one where I have the I hats, the J hats, and K hats. So I'm going to have that horrible mess dotted with that second horrible mess. And I'm talking about basically this and this going in here and here. What I'm going to do when I get that is the first term is going to be AX times BX. Actually, it's going to be AX I hat plus or times BX I hat. But it turns out this dot product is a linear operator. So I'll say dot is a linear operator. And what that means is the operation is between vectors, and you can take any scalars and pull them inside and outside of the dot product anytime you want. So what I'm really going to do is instead of having AX I hat dotted with BX I hat, I'm going to go ahead and write the AX first and then the BX, and then I'm just going to write I hat dot I hat. Well, I can tell you that the dot product is something that we use to find a component that is parallel to the other vector. So when you're doing A dot B, you're looking for the part of A that's parallel to B or the part of B that's parallel to A. So you might guess that I hat dot I hat should give you 1. And in fact, that would be the result. Alternatively, you could also just imagine that the I vector is literally just 1 with an I hat in front of it. And the B vector if that's the one, if that's the I hat as well, then it's just 1 dot I hat as well. But anyways, the I hat dot I hat is going to be equal to 1. Then the second term is going to be AX BY, and that's going to be I hat dot J hat. Okay. Well, if the dot product is made to find components that are parallel, there's no components that are parallel here. So that's going to be 0. Similarly, for AX BZ, I hat dot K hat, that is going to be 0 as well. And I think you can see that's also going to be the case when I go to the next term, which I'm now using AY. AYBX is going to be J hat, excuse me, dot I hat. Well, nothing about them are parallel, so that's going to be 0. And now I can go and do AYBY, and that's going to be J hat dot J hat. Well, that's just going to be 1. So that works out quite nicely. Plus, now I'm going to do AYBZ, and that's, of course, going to be J hat dot K hat, but nothing of them is parallel. So that's going to be 0. And you're going to get basically just a bunch of zeros, just like I show there, until finally you get to AZ BZ K hat dot K hat. And that, of course, like before, is 1. So ultimately, we learn that A dot B is AX BX plus AY BY plus AZ BZ. And remember, these are really subscripts. They're not being multiplied by me, no matter how big I write it. So that's a formula for calculating a dot product. Okay. You can also make use of it by, there's another way of calculating the dot product. Anybody have any questions on this before I move to the next slide? And actually, by the way, let me go ahead and circle this formula, because this is actually our work formula for non-constant forces. Okay. Now I'm going to show you another version of A dot B. So let's imagine for a second that A just switched to green for some reason, but that's what we're going to do. So let's say A is that vector, and let's say B is this vector, and I've put them tail to tail. Okay. Then it turns out that A dot B is in fact equal to the magnitude of A times the magnitude of B. That's what that absolute value bars mean, times the cosine of the small angle between them when they're tail to tail. Obviously, there's a bigger angle that's, when added to theta gives you 360. That's not the one we're looking for. We're looking for the small angle, and it's when they're tail to tail. Okay. So that's another formula, but we don't always have to write all that crap. We can just call this A times B times cosine theta, and that makes it look a lot easier. Now, if you look at what we just did a second ago, I dot I should be equal to J dot J, and that should be equal to K hat dot K hat, because each of them have a magnitude of 1, and each of them are separated by an angle 0. So this is cosine of 0 degrees, and that, of course, gives you 1. So that's why we were able to say that I hat dot I hat is 1, J hat dot J hat is 1, and K hat dot K hat is 1. Okay. We can also examine the other ones where we had I hat dot J hat, which is actually the same thing as I hat dot K hat, which is also the same thing as J hat dot K hat, which is also the same thing of several other combinations, because you can put them in either order, since A times B is the same as B times A. And in fact, it's going to be 1 times the cosine of 90 degrees. And the cosine of 90 degrees is what?
0.
0. So that's why we got the zeros in here. As you can see, let's say I'll underline these with blue. So you can see that's where those zeros came from. So that's another version. And if you look at the diagram here, check this out. If I draw a line perpendicular to B, okay, then I've just formed a right triangle. And in fact, this guy right here is the component of A parallel to B. And it's given by A times the cosine of theta. So you can see another way of writing this is A parallel to B times B. Also, you could draw a line, say, perpendicular to A. And in that case, you would see that this theta times B would actually give you the component of B. Let's do it in red. This is the component of B parallel to A, and that's equal to B cosine theta. So you could also say it's equal to B parallel times A. So that's some of the stuff that dot products get you, okay? It's ways that you can use it. For instance, if you have two vectors that are tail to tail and you know them in IJK notation, you can take their dot product by using this formula. And then you can set that equal to A times B times the cosine of theta. Since you know A and B, you can then solve for the cosine of theta, take the inverse cosine, and that'll give you the angle between them. So that's another trick you can do. So it's just a lot of stuff that comes in handy. Not only that, did someone have a question? I thought I might have heard somebody. Not only that, you can define a quantity called the projection of A onto B, and that's a vector quantity. It's called the projection of A onto B. In other words, it's a vector that is parallel to B and has a length equal to the component of A parallel to B. Okay. So the formula for that, in fact, is you might guess A dot B is going to be coming in handy because that gives us A cosine theta, which is the length of the component of A parallel to B. But it also gives us B, so that's kind of crappy. We really don't want that. Whereas in work, we did want that because we wanted the distance to be taken into account too, not just the force component parallel to it. So I put a B here. But now it's a scalar product divided by a scalar, so it's just a scalar, and we wanted a vector. Well, we know the vector should be parallel to B, so we might say, well, I'll write B here. Well, that's all well and good, but the whole reason you divided by B was to get rid of the magnitude of B, and you just multiplied by another B to get another magnitude of B. So in order for you to do that, you really need to multiply by B squared in the bottom. And in fact, that's it. That's the actual formula. A dot B over B squared times B. That's the projection. Because really what's going on there is one of those B's in the B squared is being divided into B. And if you take any vector and divide it by its magnitude, then you get a unit vector. So for instance, B hat is defined to be B divided by the magnitude of B, which you might also write in case you get confused later as B like that. So that's another useful thing about the dot product is it happens to allow you to do things like projection of A onto A, A onto B. The other thing that I like about it is I always hated the law of cosines. The law of sines made sense. That was easy enough. But the law of cosines made no sense because I couldn't figure out what angle they were talking about. Sometimes I thought I saw it with a minus in it. Sometimes I thought I saw it with a plus in it. Well, this is really easy peasy. Watch this. I'm going to write a vector A. Whoa. I'm going to write a vector A. And then I'm going to write a vector B parallel to that. Or excuse me, not parallel to that. I'm going to write a vector B tail to that. Okay. And this will be the angle theta. Now I'm going to be smart and I'm going to actually consider the addition of A plus B to be a new vector C. So I'm going to slide A over here. And it's going to be right there. Now I can see that this new vector C, which is equal to A plus B, since this is also A, by the way, that new vector C is A plus B. Not only that, because the way I work this, I know that this angle right here is theta. So I have some sense of what the angle theta is with respect to the dot product. So now I can take C dot C, and that's going to be equal to, God, I hate this thing. That's going to be equal to C squared, but it's also going to be equal to A plus B dotted with A plus B. So I'm going to get C squared, which literally means C times the cosine of 0, but cosine of 0 is 1. So that's why I'm saying that it's C squared. Well, A dot A is just going to give me A squared, and then B dot B is just going to give me B squared. So I'm doing FOIL, but I'm not doing it in the order that you are used to. I'm actually doing it in the order so you see the similarities between it and the Pythagorean theorem. So I've now done A and B, but now I need to do A dot B and B dot A. So it'd be plus A. Whoa, what happened there? It'll be A dot B plus B dot A. But you can tell from the formulas before that A times B is the same as B times A. So I can just write a 2 in front of that. And now I've got C squared is equal to A squared plus B squared plus 2 AB cosine theta. That's one form that I've seen expressed as the law of cosines. I really don't know what the formal law rule is because it's been so long since I had trig. But if it's that, then yay, that's great. We know what theta is, and it's not an angle inside it. But what's often done, if I remember correctly, is it turns out if you take the supplementary angle to theta, in other words, the complementary angle is what's added to theta to give 90. The supplementary angle is what's added to theta to give 180. In other words, the supplement to theta would be this angle right here, which I'll call phi. And notice that's opposite C. So you might even say that you have C squared equals A squared plus B squared minus 2AB cosine phi. Both of those are things that I consider basically the law of cosines. Okay. And now, because you know exactly where they came from, you will never make the mistake of what angle's what and whether the sign's positive or negative, that sort of thing. So if you just replace the theta with 180 minus theta, that would have given you phi. And then there's a trig identity that relates that to another cosine. And that's what I pulled off when I went from the first version to the second version. So that's some of the cool stuff about dot products. Now, that's a good review of dot products. And usually you're going to deal with them as A, B, cosine theta, but occasionally a book will ask you, hey, here's a vector A and they'll give it to you in IJK notation. Here's a vector B and they give it to you in IJK notation, in which case you're just going to use this version of the formula down here in the bottom left corner and calculate a dot product with it. Okay, so that's enough of that. Now I want to show you an example of work equals the integral of f dot dl. So let's do it for a force that's not constant. In this case, I'm going to say work is equal to the integral of f dot dl. And I'm going to introduce you to something called Hooke's law. So if you imagine a spring, and the reason we're doing a spring, this actually is true for all objects, an iron rod, a 2x4 made out of wood, but we just have to do huge forces and see small stretches if we're using those things. But if you do it with a spring, it's pretty straightforward. So I'm going to imagine a spring sitting on basically an ice skating ring. So here's my spring. And that spring has, that spring has a certain stiffness that is called the spring constant, K. And in fact, it also has sort of a equilibrium point, which I'll say is right there. And I'll say, this is my x-axis and this is my y-axis. And when x is at 0, it's in equilibrium, it's comfortable. Well, Hooke's law says that the force that the spring applies I don't know why I wrote an X there. The force that the spring applies is equal to the negative of K times X. Now, why is it negative? Well, notice if I stretch that spring to the right, then my X is going to be a positive quantity, let's say X final, and the force is actually going to push to the left. So that's what that negative is for, is to remind you that the spring force is actually a restorative force. And in fact, if you were to squish the spring, then you'd be pushing it into the negative X direction, and then a negative times a negative gives you positive. And that way, Hooke's law would say the force is in the positive direction. So it all works out. So what I'm going to do is, just like I did with lifting that mass, I'm going to imagine applying just the right amount of force to the spring to cancel out what Hooke's law is doing to me, and then just do an infinitesimal amount more so I don't speed it up. If that's the case, then at every point X, my force is going to be K times X. So the work done by me will be equal to the integral of K times X in the I hat direction, dotted with, here's your DL, it's a differential change in X pointing in the I direction. Now, when you're doing a line integral, you're supposed to either use the range of integration or the DL vector to choose the direction you're going. Once you choose one, the other one just points in the positive coordinate direction. So that's what I'm going to do here. I've chosen the DL, which is dx I hat, to point in the direction I'm going. So I'm going to use the range of integration just from small value to large value. So I'm going to integrate it from X equals 0 to X final. Okay. Now, again, we learned that the dot product is a vector product. So I'm actually going to have K times X times dx times I hat dot I hat. And you see that this is in fact just 1. So I end up getting 1/2 K X squared as my integral. And I evaluate that from X to X, from 0 to X final. So in fact, the work done by me is 1/2 K X squared. And that's actually a new formula. Work done on a spring is 1/2 K X squared. That's a new formula we can use, and that's how a line integral is actually implemented. Notice by putting in the KX, I am assigning to the force, the actual force that it has at each position X along the path. And I've taken a differential of the path, which points in the X direction. So I'm automatically getting a tangent vector. So that's really what that is. Now, the last thing I want to show you is I got to quickly, because it's actually 6:20 now, I'm going to show you the work energy theorem. So let's take the work net, and everybody's free to go. It's 6:20 now. So you're actually, hold on, we go to 6:40. Never mind. Good. Whew, that scared me. I thought everything was going bad. Okay, cool. So we now have our result, work for a non-constant force. Now your book does give you a force as a function of position X as an example in a whole section of chapter 7. Look over that. I think that's completely a nice example, and it's fairly trivial. I wanted to show you something a little bit more robust by explaining this to you, explaining that it's a line integral and all that good stuff. We're going to be using a lot of line integrals this semester, but really next semester. So you'll get plenty of opportunity to do that. Now that I have that, I have a formula that can be thought of as the work put into a spring to stretch it from x equals 0, the equilibrium position, to some new x final. Whatever that x is, you just put an x there, okay? Now, just like we thought of that work done and me lifting a box from height 0 to a height h was mgh, we also thought of that as being a change in potential energy. Well, this too is a change in potential energy. So you can also say that the potential energy of a spring, which might be represented by P, it might be represented by T, and it might be represented by U, okay? Actually, not T, I remember now. I think T, when they did use that, they used it for kinetic energy, which was kind of weird, but they might use it for V. But either way, it's 1/2 k x squared. And you can think of that as another way of what this is. Obviously, it takes an amount of work, 1/2 k x squared, to stretch it or compress it a distance x from its equilibrium. Another way of thinking about it is if you have a toy that's like a spring-loaded launcher, like you probably had when you were a kid, if you compress that spring in a distance x, it's sitting there and it's cocked and it's waiting for the spring to be let go. At that point in time, it has a potential energy equal to 1/2 k x squared. So at any instant, that potential energy could be let out and converted, say, into kinetic energy, which would make the object take off with some speed, and it would shoot up until the kinetic energy it had been converted to potential energy, mgh, in height, and that's why it came to a stop. And then, of course, at that point, it's got potential energy and 0 kinetic energy, and gravity is going to start to pull it back down, and it will, in fact, land on the ground with the exact same kinetic energy that it had before. So we're going to see there's a couple types of energy. You've now seen potential energy due to gravity. That's a positional potential energy. And now you've seen positional potential energy due to position connected to a spring, okay? Now, it turns out there's also an energy of motion that is another form of mechanical energy, and that's what we call kinetic energy. And I'm going to derive that for you by basically deriving the work energy theorem. So let's start that now. So here's the work energy theorem. And this work energy theorem, by the way, is sort of what police officers are using if they go to a wreck scene and are measuring the skid marks for a wreck, because they basically are saying, okay, well, a certain amount of work was done by the friction between the tires and the road and leaving the skid mark. Well, that work is actually equal to the change in kinetic energy of the car. So they can use that to find out what the kinetic energy of the car was when it started skidding. And if you know the kinetic energy it had when it started skidding, that's just mass away from figuring out what its velocity was. And therefore you can tell if they're speeding. So that's kind of neat. So let's start off with something like work net. This is the total work done by something. We also might call it work total. That's perfectly fine. But what it's going to be is the integral of the summation of all the forces dotted with dl. Does anybody recognize that summation of forces? What does that look like to you guys?
Like net force?
Mm-hmm. Was that on a law that we've seen before?
Newton's second law, I believe.
Exactly. So what we're going to do now is we're going to take that integral and we're going to replace that sigma f with m times dv dt. Why dv dt? Does anybody recall?
Acceleration.
Exactly, because F equals ma is what we're using, only we're using sigma F because it's the sum of all the forces. So yeah, exactly. Well, it turns out that these little dVs and dLs and dTs, they're not just symbols, they're actually things. And if you had like a really high level Calc 3 course or a vector calculus course or a differential forms course, you would learn that these things are like differential forms or one forms or stuff like that. So you can actually move them around. And in fact, when you use them to work out chain rules, that's because they're real things by themselves. It's not just convenient. It really, these are entities. So what I'm going to do is I'm going to trade the DL and the DV, and I'm going to say equals the integral of M dl dt. It's a horrible looking, dotted with dv, excuse me. I don't like any way that wrote. Take all that away. Okay, m dl dt dotted with dv. Okay. What is dl dt? Does anybody recognize that?
Velocity.
Exactly. So we've got mv dv, or dotted with dv, and I think you can tell what that means. That means we're going to have a 1/2 m v squared evaluated from, let's say, v initial to v final. So that's going to be 1/2 m v final squared minus v initial squared, or in other words, the net work done is equal to the change in kinetic energy, where K equals KE is defined to be 1/2 m v squared. So that's the work energy theorem. So if you sum up all the forces acting on something and calculate all the works done by them throughout some time period, whatever that number comes out to be, that will be equal to the change in kinetic energy of the object. Okay, so we've now defined a quantity called kinetic energy, which is 1/2 mv squared. You can see it's proportional to mass. So for instance, a small car and a large car, if the large car is twice as massive, even if they're both going 30 miles per hour, the large car will have twice the kinetic energy. However, if two cars of the same mass, one's going 30 and the other one's going 60, the one going 60 will have 4 times the kinetic energy as the one going 30. Okay, and therefore you're going to need 4 times as large a braking distance to come to a stop. So that's the disadvantage of going 70 in a 35-mile-per-hour school zone. You have to take 4 times as much distance to stop. And we'll do an example like that, or you'll see some anyways. But first off, let me work an example. Let's imagine, I'm going to first start off with the work problem. So let's imagine we have a box whose mass is 30.0 kilograms. I'm going to apply a force of 100.0 newtons at 37 degrees in an attempt to pull it along a floor whose coefficient of friction is 0.20. Okay. What I would like to know is I would like to know what is the work done by the force I applied, the work done by the friction, the work done by
the normal force and the work done by the gravitational force. Okay. And then I'm going to calculate W total, which is in fact the same thing as W net that we just talked about. Okay. So one thing is I can draw a free body diagram, and part of this whole thing with work and energy is bypassing vectors. You don't have to do as much with vectors if you're not using Newton's second law. You're using energy methods, which are scalars, and that's part of the advantage, but you still have some areas where you have to work with vectors. So for instance, I'm going to draw a coordinate system. This is my x-axis, this is my y-axis, this is my mass of 30.0 kilograms. And in fact, I have a force of 100.0 newtons at 37 degrees. Well, that just reeks of 37 degrees, just reeks of a 3-4-5 triangle. And in fact, we know that 37 degrees is opposite the small side because it's less than 45. So I can immediately say that this component of that is in fact, since 5 times 20 is 100, this must be 3 times 20 newtons, which is 60 newtons. Okay. And I can tell you that this component must be 4 times 20 newtons, which equals 80.0 newtons. Okay, so I've already worked that out. I know that there's going to be a normal force upward, Fn. I know that there's going to be a weight pointing downward, and that is 30 times 9.8, which I believe, someone please check me on this, is 294 newtons downward. And in fact, there's going to be a friction force F, which is equal to mu K times the normal force. So if I take the summation, if I take the summation of the forces in the y direction equals mass times acceleration in the y direction, and realize that this box isn't going to be bouncing up and down, so the acceleration is going to be 0 in the y direction, then I get Fn plus 60 newtons minus 294. Did anybody verify that? Is equal
That's
to,
correct.
okay, thank you, is equal to 0. So that allows me to determine that F normal is in fact 234 newtons. Okay. Now, what I know is that the work done by my force is equal to, these forces are constant, even though they still make an angle. So it's going to be my force, but the component parallel to the distance. And I completely forgot to tell you what the distance was, stupid me. So the distance we're traveling is D equals 100.0 meters. Okay, and it's horizontal. So I'm just going to take the component of F parallel to D and multiply it by D. Well, the component of F parallel to D is just that 80 newtons. So I'm going to say 80.0 newtons times 100.0 meters. And I'm going to get the work done by me is equal to, notice the cosine in this case would be cosine of 0. Because basically I could have used the cosine of 37, but that's how I got the 80 anyways. So either one of those works out for works out to do it. So this is going to be 8.00 times 10 to the third joules of work done by me. Okay. Now, what is the work done by the friction force? The work done by the friction force is equal to the friction force component parallel times D. Well, notice the component parallel is actually the whole force itself. So I'm going to go ahead and write in there that it's 0.20, because that's the coefficient of static friction or kinetic friction, times the normal force, which we found was 234 newtons, times D, which is 100.0 meters. Now here's the kicker. F points to the left and D points to the right. So cosine should be cosine of 180 degrees, which is -1. And I think you can see that this is going to be 468, or excuse me, 46.8 times 100. So 4680 joules, and it's going to be negative. So the work done by friction is equal to negative 4.68 times 10 to the third joules. Okay. Now that's negative, and that's what you expect. Whenever the force appears to be losing, in other words, the force is pointing to the left, but the object's going to the right, that should be an indicator, hey, this is negative work. This is thing that's sucking energy out of the system, right? If you do the work due to the normal force, work due to the normal force is going to be the normal force, which you found was 234 newtons, times the 100.0 meters, times the cosine of 90 degrees, which is just 0. And I think you can figure out what the work due to gravity is. That's going to be, of course, 294 newtons times 100.0 newtons times the cosine of 90 degrees as well, which gives us 0 again. So work total, dang it, I keep doing that. Work net is actually equal to 8.00 times 10 to the third joules minus 4.68 times 10 to the third joules, which gives me 3.32. Be 7, 9. Yeah, 3.32 times 10 to the third joules. And according to the work energy theorem, that's how much the kinetic energy would change. So if you actually applied that force, you could say, wait a second, this is force times distance is equal to 3.32 times 10 to the third joules. And we're going to say that's equal to 1/2 mv squared minus 1/2 mv0 squared, which is, this is just 0 because we're assuming it started from rest. You would find that, in fact, this gives you exactly the velocity you'd have if you calculated what the acceleration of this block would be and then let it accelerate for a distance of 100 meters. You get still the same answer as this. That's something I would like you to try for extra credit if you want. So again, just so I can word it properly, for extra credit, you can take this energy, this 3.32 times 10 to the third, assuming I did that arithmetic correctly, okay? You can say that's equal to the change in kinetic energy, which is just 1/2 times 30 kilograms times V final squared, and solve that for V final, okay? So you're going to solve for V final. And then you're going to use Newton's second law to attack this X dimension, because we've got a force going to the right of 80 newtons, and we got a friction force of, I think I found 0.2 times 23.4
or excuse me, 234. So that's going to be 46.8. So 80 minus 46.8 newtons is the force in the X direction. That's the total force. That's equal to 30 kilograms times A. So you can solve for A. And then you say, okay, A is this, V0 is this. What's the final velocity? And I think you'll find that it's the same final velocity in both cases. Okay. So please, by all means, write that up, submit it for an extra credit, and it'll count as 100 to replace one of your low or missed homework scores. Now, we've essentially done everything that I really wanted to do here. I've given you enough examples of how to calculate work and energy, potential energy, kinetic energy. The only thing I'd do now is probably work a problem like, let's say a car left 100 meter or 15 meter skid mark, and the coefficient of friction was 0.22, and the car had a mass of 1,000 kilograms. What in fact was its initial velocity? So you could do that again with the work done by friction, which is mu times the normal force times the distance traveled as a vector, which would be 15 meters, times cosine of 180. So that give you a negative. That's equal to 1/2 m v final squared, where v final is 0, minus 1/2 m v initial squared, where v initial is what you're solving for. Solve for v initial, and that allows you to actually determine the initial velocity of the car just by knowing the length of the skid mark. So that's the only other problem I would have worked for you guys had I given enough time, but I'll probably do that next time anyways. But I think you have plenty of time to, or plenty of the concepts and examples here between this and the book to do all of chapter 7 easy peasy. Okay. Everybody's free to go. I'll wait for the last person to leave, and I'm also going to field questions if anybody has them. Thanks for coming,
So
everybody.
Did you say for the extra credit, you were saying work through this problem and solve for VF?
I'm going to stop sharing. Does anybody need me to keep this before I stop sharing, or can I go ahead and let that do?
Yeah, I had a question about it if you could wait.
Okay.
Oh, Professor, that thing you were sharing, I was gonna.
Anybody have any questions?
Yes,
Yes.
Professor.
Somebody asked about the extra credit first.
Still a lot of people here. You're welcome to ask.
Can you hear us?
I don't
Professor,
think
can you
you
not
can
hear
hear
us?
us.
I'm gonna go ahead and start exporting this to my Google Docs. Which of course anybody can have access to. All they have to do is email me and ask me, but you guys are in my class, so you just have to look on Canvas and find the actual notes.
Professor,
I'm saving it to my 241 folder.
can you
And it's
other
uploading
students
now.
hear me?
I can hear you.
So a lot of
can
people
hear
here.
us.
Anybody have any questions?
Yeah, yes, I'm
See
raising
Mike,
my
see
hand.
William.
What reactions at them?
Professor,
Do
can you
y'all
check
need to
the
see
chat?
anything on my notes before you go? I'm fine to help you with that. Jamie, I like
I'm
the
sorry.
face
This
there.
is so annoying.
It's always something.
Would you like?
I saw
You
something
can
that said
stick
he has
around and
dealing
just
with
ask
some
me
low
questions you
bandwidth.
have.
So.
You can't. Oh, I can't hear you. You know, I did notice that I hit Paul mute or something earlier. I'm sorry. I saw that and I was like, nah, I didn't see what I saw, but I saw what I saw.
Oh my God.
I can hear you now.
Can you hear us now?
I can. I'm so sorry, everybody. I hit something with
You
my
can hear us now?
iPad, and yeah, I do. I'd seen it put up a microphone. I didn't think anything of it, but yeah, now I see. I definitely muted it. That makes a lot more sense why y'all just sitting around. So please give me a question, and I apologize.
Sorry, I had a question about the extra credit.
Uh-huh.
You're saying so just work through that particular problem that you had up at the end and then solve for VF. Was that right?
Yeah. Solve for the final velocity, and you'll see how basically you come out with the exact same result, whether you do it with Newton's second law or with energy methods.
Well, I had a question. Can you, if you could share, it was, you closed it. We were trying to get you to keep it up.
Yeah, absolutely. I was just getting ready to offer that because I figured that had happened. Such I couldn't hear you. There you go. So is this part what you want to see, or is a previous page?
Yes, so this is more for my understanding. So let's say like the work of the force and the work of friction, I guess.
Mm-hmm.
No. The normal force and the gravitational force. So let's say that that thing was on like an incline. Would that be would we have to find the angle of the incline, and that would be the cosine of that?
Yeah, if you were doing the same problem on an incline, then you'd probably want to do a tilted coordinate system parallel to the incline. And then you'd have a component of weight that's pulling it down the incline, but then a component of weight that's perpendicular, and that's contributing to the normal force. So all that stuff would have to be redone, but it would actually be something that you could do. It's just they would have to give you the angle of the incline. Or they could ask you to solve for the angle of the incline, but they have to give you some other variables so you can do that.
Okay, so that would help me out for the normal force, but would I use that same incline for the gravitational force, or would that still be zero?
Yeah, the gravitational force would then break up into a component that basically gravity always points straight down. But if it's along an incline, you can imagine that straight down vector is created by a vector parallel to the incline and another vector added to it that's perpendicular to the incline, ending up with a straight vertical vector. So those vector components of weight in the X and Y tilted coordinate system are going to contribute to your normal force in the case of the normal one, and contribute to a force compelling it to roll downhill in the case of the parallel one.
That one would still be zero.
The what would still be zero?
The gravitational force, the work,
Yeah.
gravitational work.
In that case, it actually the work would be positive because, well, it'd be positive if you were going downhill. If you were going uphill, then the work would be would actually be negative. But again, if the gravity, which is pulling downhill, if you're going downhill, that's going to give you a positive work. If you're going uphill, the gravity would give you a negative work.
Yeah, so I guess that's what I'm asking. Like, what if I'm pulling it uphill, I would get, I guess, a negative value because it's restricting against it. But I'm saying, what angle would I use?
Okay, so in that case, you're talking about the component of weight parallel to the surface, which would be mg sine theta. That
Okay.
mg sine theta is the force, and that's going, let's say, down the hill. The d would be 100 meters up the hill, and then the theta would be 180 degrees.
Okay, and cosine theta is, or cosine 180 is -1. Okay,
Exactly. That's where that comes from.
okay, awesome. Thank you.
No problem. Anybody else?
I have a quick question about, sorry.
Go ahead, Mike, and I'll get to the next person next.
I have a question. Hey, so Monday is a holiday. Are we still doing Zoom?
Monday is what? It's not a holiday recognized by TCC.
Okay.
So I'll still be holding class. But if you can, I mean, it's fine. You'll just catch the video.
No, that's fine. I just want to make sure.
Yeah, I don't take off for missing classes except in lab.
Okay.
Okay,
All right. Thank you.
no problem. Anyone else? Famada, you stole my gig. All right, I'm going to go ahead and on this backside, I'm going to articulate that problem that I suggested for extra credit a little better. I guess I should have done that before I sent no, I'll just type it up in Canvas and let it go with that. So I'll actually type that up in the extra credit box for the assignment area for the extra credit, and that'll explain it. Okay. You have a good one. I'm going to stop sharing, and then I'm going to exit stage right. Heavens to Megatroid. All right. See you, folks. Last call. Good night, Famada.